All right, Paul, so you've shown how you can get all of the mass into the center, so presumably that's going to be the star. And then we have this disk, this thin disk of stuff, of dust and gas, but we don't have planets yet. So I can imagine how you might have the little bits of dust through van der Waals forces conglomerate to make tiny little particles, but how do we go on from there?
Yep, so the idea is this disk could be mostly gas and a little bit of dust. The dust grains are made of the heavy elements, and they will indeed stick together by van der Waals forces, the chemical forces. And so they might get up to the size of grains of sand, and then the grains of sand might stick together and form boulders, maybe the size of cars. And then they might start smashing together to form maybe things the size of mountains, and then they might in turn smash together and form things the size of moons. And as time goes on, you get fewer and fewer things that are bigger and bigger smashing together until eventually it all just stops because the things that are left are quite big. They're called planets. And they're now so far apart that the average time between collisions is bigger than the age of the solar system.
Now, I can imagine there might be a few problems with this. There was a lot of ifs and buts in your description.
And there absolutely are.
The first problem is the sticking procedure. When grains are really small, like atomic size or molecular size, they will indeed stick together by chemical forces, the van der Waals force in particular. When they've reached the size of moons or asteroids, then gravity will suck them together. The real problem comes in the intermediate stage, when these grains are the size of, say, sand or gravel. How do these things stick together?
So, do things the size of grains of sand or gravel stick? Well, let's try it. Here we have some gravel. I'm going to imagine it's flying around the solar system and see if it sticks together. Let's try it. It didn't stick.
So, our first problem. It's easy to form tiny little grains, molecule size. But then, once they get to the size of sand or gravel, how do they stick together to form the bigger ones? Once they get to things the size of boulders, they can stick together from gravity. But there's a barrier. We can go from atoms to sand. Once we've got boulders, we can go to planets. But how do we bridge the gap in the middle here? How do we go from grains of sand to things the size of boulders when sand and gravel does not stick? Well, that's the first problem, and it's an unsolved one. But there is a second problem, which is disk drag. What's this? Well, let's have an edge-on view of our protoplanetary disk. We've got the star in the middle, and we've got a layer of gas, and inside it are lumps of stuff of different sizes, which are the grains that are going to end up forming the planets, etc., etc. And the whole disk is spinning round at some speed. Now consider one of these lumps. It's moving in a circle at velocity v, so there must be a force towards the middle, a centripetal force, given by the usual equation mv squared over r. And for a big solid lump, like a planet or a boulder or something like that, that will be given by gravity. So it's equal to Newton's gravity, gmm over r squared, which means we get a velocity, as we've worked out before, of root gm over r. All straightforward, we've seen that before. But now, instead of looking at the particles, let's take a square of the gas, or a cube of the gas, or something like this. Now the gas is also spinning around the star at some speed v gas, and it also needs a force towards the middle given by mv squared over r. Anything moving in a circle, whatever it's made of, requires a force to keep it moving there. The difference comes in what the force is that's making it move towards the centre. There's going to be gravity, g m over r squared, just as there is for the lumps. But in addition, there's going to be a pressure force. Consider this disk. The inner regions are going to be more dense and probably hotter. Further out, it's going to be less dense and probably colder. When gas is hot and dense, it's high pressure. And likewise low pressure further out. So if you consider a bit of gas somewhere in the middle, like this one down here, the gas on this side is going to be hotter and denser, the gas on this side is going to be colder, so the pressure from this is going to be stronger than the pressure from that. So it turns out there'll be a net pressure force which will push outwards. So what this means is, in addition to the gmm over r squared going inwards, you've got some sort of delta pressure pushing outwards, which will partially cancel out the gravity. It won't win, the gravity is a much stronger force. What it means is the force towards the middle is a bit less than gmm over r squared. So the force is going to be less than gmm over r squared, just a little bit less, which means that the velocity will be less, a little bit less, than root g m over r, the normal orbital speed. Okay, so lumps travelling at orbital speed, gas travelling a little bit slower. Now you might think, don't the lumps get affected by pressure? And the answer is they do. If you've got a lump of something, it too will have more pressure coming in than out. But lumps are very dense, a lot of mass, not much surface area, so it turns out the pressure has a relatively little effect, because pressure depends on surface area, not on mass. So what does this mean? What it means is that the lumps are going to be travelling faster than the gas. So as they go round and round, they'll be exposed to a headwind. Now this is a problem. If you're a really big lump, like a planet or something the size of a mountain, you've got a lot of mass, not much surface area, so you can kind of ignore the headwind, and you'll just, because the protoplanetary disk, the gas is very tenuous, so you can fly through and ignore things at your orbital speed. If, on the other hand, you're a really tiny grain, like sand or atoms, in this case, you don't weigh very much, so the gas around you will dominate your motion. It'll be carried around like the wind, just like a sandstorm or a dust storm or something like that. So in this case, you'll be travelling at this speed and quite happy. The trouble comes when you get things of middle sizes, boulders. They are affected by the drag, the wind relative to them moving backwards. They're not massive enough to ignore it. So what this means is they will be slowed down a little bit below the speed, which means centrifugal force will not balance gravity for them, which means they will spiral in. So they will go inwards and inwards and inwards and inwards and inwards until they fall into the star. And you can calculate how rapidly this happens. You work out the pressures and temperatures of the gas as you go out. You therefore work out the pressure force, how much the gas speed is less, by how much it's less than the orbital speed, what the drag is on a rock of a given size, and it turns out that the time needed to fall into the middle is very small, much smaller than the time it would take before these boulder-sized rocks smash into other boulder-sized rocks and make something big enough that can ignore the wind. So, problem number one, the sand and gravel do not stick. So you can form subatomic particles up to the size of gravel, but then nothing should happen then. If you do make it up to the size of boulders, they should fall into the sun pretty fast. Problem number two. Somehow we have to get over these two problems, get things up to the size of mountains, and then we can let them collide together and go all the way up to the size of planets.